Sup folks, Alex here. So today I really wanted to play a little bit with the md5 hash sum algorithm, right? So as a result of today's video, we should be able to understand how it works, roughly understand. Should be able to just re-implement it in Rust. And as a bonus point, I want to play with md5sum utility from core utils, right? So md5sum util, if you haven't heard of it, so it's basically an util that would take your input either from the standard input or as a file, right? And it would compute the md5 hash sum for you and print it back, basically, right? So I could have done that, but I could have done something like binls or something. So this is a hash sum of my binls on that machine. So we are, we'll be trying to do something similar to that. So let's go ahead and read a little bit on md5. So md5 is a message digest algorithm, which is, by the way, still widely used. And we will see that it's not necessarily a good idea to still use it, and it's a fairly old algorithm as well. So it's been specified in 1992 in that RFC. So the input to that algorithm is a buffer of any length, of course, right? But the output would be exactly 128-bit each time, right? And the algorithm itself is based on something known as Merkle-Damgard construction. So Merkle-Damgard construction is a method of building collision resistance, cryptographic hash functions from collision resistant one-way compression functions. So it sounds fancy, but not really, right? So basically, like, the whole premise here is that if you were to compute a hash function of your message using that approach, you would split your message into n chunks of equal size, right? And you would probably need to pad the very last of the chunks, right? And then you would need to come up with some kind of function f, right? You would need to carefully design that function f, also called compression function, right? That would take a block. So for md5, the block size will be 512-bit, right? And it will, compress that block. Again, in md5 case, it would compress 64 bytes into 16 bytes, but it would also scramble the contents of that block, beyond belief, basically. And you would do that many times, right? For each block of your message, right? It can be many of these, and on each step you would take the actual block, right, and the result of the previous block, and use that result as a kind of a salt for that, right? And basically, when you run out of blocks, you will get your final 16 bytes, in the context of md5, and that would be your result, right? And of course, the whole complexity and the whole kind of all the nice properties of hash functions lay within that f function, right? So that's that. Okay, so history, cryptanalysis and stuff. So on security, you guys know that md5 is broken beyond belief, but md5 fails all the requirements catastrophically, and it's being considered cryptographically broken, unsuitable for anything. So although I think the actual pre-image attack is still kind of infeasible, right? So if you need to come up with a message that would hash to a particular md5 hash, that thing is still infeasible, I think, but don't quote me on that, but I think so. So that would that would mean that if you only need to kind of fingerprint your message, and if you don't really expect an attack on that, right, then probably md5 is still fine. But also, why would you use it, right? We have SHA-2, we have SHA-3, we have Catsack, we have Blake family as well, something like Blake 3, extremely high performance, blazingly fast, right? Written in Rust, actually. yeah, it can utilize all your cores, it can utilize SIMD, it's like, you know, state of the art basically. So why would you use MD5? I don't know. So the only part we're interested here is actually this. So this is kind of an Algol 68 inspired pseudocode of that algorithm. So yeah, I mean, the algorithm itself, you know, just, you know, glossing over it, you can see that it's, you know, fairly simple, right? So before we start to compute anything, we actually initialize these for kind of registers. Each register is 30-bit long, right? And for the matter of fact, you know, those registers are actually directly involved in you know, computing the actual result, right? So the actual result is just a concatenation of those registers. So that's that. And then basically you take your message, you split it into 512 chunks, bit chunks, and you would use those chunks and, you know, some you know, predefined constants and whatnot to basically like produce a white noise from that message. And that white noise is supposed to be, even though it's like an actual white noise, right? So there is no structure to it. That white noise is still in a very high correlation between, like, to the original message, right? And that's very important because, for example, here, right? So the MD5 hash of that message is this, but should you add like a dot at the end, or you could flip like just a single bit somewhere, you know, in between, the result is very different, right? So due to something known as avalanche effect, the result is supposed to be very, very different, and that's, you know, that's what you want basically. So that's that, and I think that listing here should be plenty enough for us to re-implement. Oh, sorry, still coughing. I had my pneumonia like a month ago or something like that, but yeah, I'm still coughing. So yeah, I mean, let's go ahead and try to re-implement that. So cargo new bin md5 sum rs. How about that? Okay, so code this. Oops. Okay, so cargo run. Yeah, so our Hello World project runs. Yeah, so I already know that I will be needing to read a file, so I'll add something. Derive, and maybe anyhow as well. Yeah. So use clap parser, and then struct options, and maybe like path is std fs, or what is it, path? Path both, right? Derive parser, right? So let options, this options parse this, right? So let's go ahead and define our kind of main entry. So function compute md5, I guess. And I want to make it generic over t, reader t. It will return something known as digest, where t is std io reader. Yeah, read. Okay. So digest is unknown. So struct digest. Okay, so what is digest? So digest is supposed to be a 16-byte long array, but you know, it's actually like four 4-byte long registers being concatenated. So I actually want to preserve that kind of structure to it. So U32, maybe 4, and then I want like 4 of these, right? And let's go ahead and impl as ref. As ref this for digest. Function as ref, ref to self 0, right? And I want to implement stt fmt this pull fmt this display for digest. So display for that, I just want to kind of, you know, keep that kind of look, right? So this is like 128-bit long, but it's actually 32 hexadecimal numbers, right? So I basically want this. So function fmt for item in self as ref concat iter map. How about that? So b format of what is it? It's like b02x, and then write like f item. Okay. So we have that. We have our main entry, and having that main entry, let's define what would be our reader. So let reader will be std fs like file open options path. I think it can fail actually, so anyhow result with this. Okay, so we have reader, but of course we actually need to wrap it with stdio buff read new implementation, otherwise it just won't be buff reader, of course. Cool. So that's that. So we have this. So how it works. Yeah, before we start doing this, we actually need a bunch of constants here as well. So let's start with this. Honestly, like I don't really have much idea of like what these actually do. So the wiki page doesn't really, you know, explain it in great details, right? It's just a floor of like sinuses of those numbers. I think it's kind of just like random-ish numbers. I don't know. So let's see. So we have like const k, which are actually U3264, I think, right? So we have this. Okay. So that would be this, that. Okay, so these are case. These are shifts, so per round shift. So const shift s is U32. 64 of these, right? And again, so shifts. Okay, so we need those initial values. We'll put them here, I think. So that would be like let mute these, and then U32. Okay, missing type. Sure. Type is here. Initialize values. And then we know that the result actually would be just these numbers, right? So let's you know, do something like this. So digest. Let's say it's like A0 to LE bytes, B0 to LE bytes, C0 to LE bytes, and D0 to LE bytes. Yeah, so yup. And what about our digests? U3244. 2 bytes should give me what I want, no? Found array of these. Oh, this is because, yes, so this is because that's not what I want, of course. I want this. Sorry about that. U8, of course. For the chest, U8, sure. Okay, cool. So having that, we could probably start testing. So let's do some TDD, haha, mod tests. So yeah, test function empty. How about that? So we have a message. Okay. So assert eq what? Assert eq like compute md5 over reader. So stt io cursor new of what? Let's say this, right? No, empty. I want empty. So of empty actually, right? And I want that to be equal to this. Oops, no, to this. Okay, so this, that, into. Okay, and it cannot be a yes because that actually to string. Yep. Fine. So that's that. And brown fox, right? So over the lazy dog. Cool. So let's take the brown fox example over the lazy dog, and for the brown fox the result should be just that. Cool. And yeah, so let's go ahead and try to test it. Cargo test. Of course it will fail. So left to right doesn't match, and it's supposed not to match just now. Okay, so here, right? What we are doing here, we have this reader, and we need to like read this reader into chunks, right? So what kind of chunks? Chunks are 512-bit long, which is 64 bytes, right? So let mute chunk is, let's say it's like it's like 0 64 times, right? And while let okay bytes read equals to reader. Okay, read into mute chunk, right? So I don't know how to implement that just yet. Reader must be mutable, of course. Fine. I think we would also need a original length in bits as well, right? So let len bits is 0, and of course it's mutable, and len bits bytes read times 8. I think that should be good. Okay. And then, you know, depending on like how many bytes we actually read from the source, so match bytes read. So if it's like 64, then it's a full we just read a full chunk, right? Let's imagine that we have like a, I don't know, process block or something, or process chunk, let's say, right? So chunk is a reference to U8 64, and we have like a 0, like we have those registers here as well, mute 32, and like that, right? So A0, B0, C0, and D0, not that, and to do this, right? Cool. So So we have those registers. We have this process chunk thingy here. If what we read is a kind of full-blown chunk, then we could just do what? We could just read this process chunk, and well, yeah, it would be just that. Do we need to modify the chunk itself? No, we don't. We don't. Mute, and then mute, right? So then, if what we read is not a full chunk, something like 61 minus 1, but I think that would be just fine, we need to pad the chunk, right? So let's see. So chunk bytes read. Let's just do this, maybe like 1b 1 2 3 4 5 6 7, right? That works. Then we need to pad it. So it's not only like not the full chunk. Oh yeah, so it's not a full chunk, but it's a kind of paddable full chunk. Okay. Paddable not full chunk. Let's see. Let's call it like this. This probably doesn't make any sense to you, but like I'm trying to like keep these cases in mind right now. So to the end, we will like fill it with zeros, right? No, actually, no. So actually that would be all the way to 56. We will fill it with zeros. And then we'll take the chunk, and from 56 onwards, we will copy from slice len bits to LE bytes, right? And then we can go ahead and compute our process chunk thingy, right? Basically, oops. Oops. Why you are not doing what I want? That's weird. Okay, so mute chunk, yeah, mute this, mute that, and these as well, right? Okay, so I think that's fine in that case. And let's see, so if it's like from, what is it, from 56 to 64, then we cannot pad it like this anymore, right? So you need to do this, right? You need to like append this, you know, 1-bit padding. You need to append whatever, how many zeros, right? Then you will get yourself a normal chunk, which you can now compute, right? Then we could have filled the whole chunk with zeros, and we could have done this, and we could have recomputed the hash of that chunk as well. And this is break, right? Break, cool. And all the other stuff, like all the other stuff, should be unreachable, of course. Bytes read. Yeah, so that part I think is done. Bits, len bits. Well, technically it's len bits module 264, but that would not make a real difference at all. So that part is unreachable, and there you go, right? So basically, like, what's left here is we need to implement the actual function here, right? So the actual function f, right? So okay. we can do that. We can definitely do that. So let mute U32, right? And we don't need that. And like that, right? But it's also like that, right? Should have snake case. Okay, snake case. Non-snake case. Fine. Cool. And then we have this loop over there. Okay, for round in from 0 to 64. Okay, and we have like this elimination. I'll copy that part. Okay, so I don't really want to rewrite it, you know, by hand. So, you know, oh, thank you. Is it what I want? Else. So rewrite using the correct Rust syntax and use match expression as well. Okay. Yeah. Thank you. Okay, except I don't really want that part, at least not now, right? Oh, so we have this FG. Well, let's assume that it's been rewritten correctly. And now we do this, right? I kind of want to do that myself. Okay. Oops. Okay, so F will be F wrapping add to F to wrapping add to A, wrapping add to K with this round, right? Wrapping add to the message, basically to the chunk, right? You know what? I actually want that chunk to be reinterpreted a little bit here. So let chunk unsafe. Well, std mem transmute of the chunk, but I really want it to be like U32 16. That would have been just easier to work with. Oops. Cool. So the last part should be what? Should be this chunk parameterized by G. And cannot mutate this. Okay, so let mute F. Okay. And then A becomes D. D becomes C. C becomes B. And B becomes B wrapping add. Left rotate F to this. So wrapping add F rotates left, I think, to shifts round. Something like that. Right? So we do this, process chunk. Is that it? Process chunk. No, that's not it, right? And we need to modify the okay, so a 0 is like a 0 wrapping add to A. So B, C, D. So B0, C0, D0, B, C, D, right? Process chunk. Let's go ahead and inline it. And yeah, process chunk. So what you're not happy with? Process chunk is never used. That's not true. It's been used. So compute md5. So compute md5 haven't been used. That's fine. We'll finish it just now. Okay, shifts never used. Yeah, that's fine. So cargo tests. Okay, so our tests are not passing. Let's see. Commute md5 length bits 20 bytes. Break. So that part looks good, right? That part looks good as well, but who knows? Maybe Copilot actually failed here. From 16 to 31. BC, not BD. Okay, so BC, B and C, not BD and D. D and what is it? D and B, not D and C, right? And 5 times round plus 1. Yes, B XOR. Yes, 3 times plus 5. C XOR B or not D. Yep. Why would you do that? Okay, F plus A plus K. F plus. So yeah, it will be like F plus. Oh, what's this? F plus A plus K round plus chunk G, right? So let's see, cargo test. Yep, that was it. So we've successfully implemented the md5 algorithm right now. So let's see how it works with the actual files. So here, let's see. Okay, so that would be like hash and like fname. So hash will be md5 compute mute reader, right? To string, and then fname would be self. It would be options path to str unwrap, right? And reader is not mutable, so let's make it mutable. Yeah, use super. Let's use everything, and let's do CFG tests, right? Cool. So still works. Let's go ahead and cargo run release. I don't know, maybe like cargo toml. Okay, so this is what we get for cargo toml from our implementation, and md5sum the same thing, right? So let's create maybe a somewhat larger file. So let's, maybe create something like this. ls minus lh data. So it's 600 megs of random data. Let's see what about performance. So data det, and the performance here is what? So it took that amount of time. Let's cargo build release. I cannot type, I don't know. So target release md5sum rs data. Okay, might be longer. So it is longer. So our implementation is slower than the core utils thingy, which I think is fine, because like core utils is very highly optimized, but I don't know. So status, right? And yeah, target as well. Okay. Cool. So the question now would be why it's so slow. So my best bet would be is that loop over there actually is slow as fuck. And well, loops are never fast, right? So let's go ahead and try rewriting it. So basically, let's go ahead and try to unroll that whole loop. Of course, I won't be able to do that myself. So I'll ask, so unroll that loop, no loop should left at the end, and use use like macros to reduce the so yeah, the repetition. Let's see. So hopefully it will just unwind everything. Oh, Jesus Christ. That's a lot. I think it's struggling. It's actually struggling. Let's try again, maybe. Yeah. Okay. Oh. Yeah, Copilot fails spectacularly. Let's try. So no loop should left at the end, and use macros to reduce the repetition. Okay, let's maybe try this. Process rounds, sure. Oh, memswap, like why would you do that? Wow, that's a weird implementation. Gotta tell you right away. ChatGPT maybe? I am a man. Okay. Okay, so please unroll that loop. No loops should left at the end. Use macros to reduce the repetition, right? All right. So it also does something. Fine. Let's try Claude then. I think Claude should be able to do this. Okay, unroll that loop. Use the use like macros to reduce the repetitions of the code. Okay. Yep. Okay. This looks good, actually. Let's see. This looks good. Let's see. So let's remove our okay. All right. No, yeah. Okay. Wow. That's a lot. That's a lot. But hey, cargo test. Yup, the tests are still there. And what about performance? So build. Yeah, let's maybe let's do the build with a bunch of optimization keys as well. I don't know. Let's see. So it used to be 1 second, 1 second and 25 milliseconds or something like that. Let's see how it performs now. So time release, yes. Okay, so it is somewhat faster, right? And so it used to be 1 second, and now it's 0.76, right? md5sum. And the core utils thingy is this, right? So we are slightly slower, right? So let's see, hyper fine, warm up like 20 and then I don't know, maybe 50. So let's do a proper measurement, I think. Yeah, let's do this. But hey, so we managed to, actually implement the md5 algorithm, right? Wasn't that hard at all. Also, I think the loop unrolling strategy actually works just fine. Yeah, so in terms of performance, we could actually try something like with, is it like with capacity, right? Capacity size. So let's do 496 times 8 maybe. So let's increase the bufferization, right? So build this, and yeah, I cannot do that. Okay. What is it? What was it? Okay, like this. And let's see. Okay, so it is slightly faster than it used to be. It used to be 760 milliseconds, I think. Now it's 750, which is good. Yeah, but like all in all, right? So what we are getting is 750 milliseconds, and the core utils is what? Is 700. So we are slightly slower, less than 10% slower, right? For the matter of fact, so it's like Python 3. Yeah, we are 750, right? 706. So it's like 6% slower than the core utils implementation, which I would say is okay, right? So the core utils implementation has received like decades of optimizations, right? It's written in C, it's like very highly optimized. So I would say it's fine. We could have maybe like spent another hour or so like optimizing that thing. Maybe we could have reached the core utils performance as well, but I don't see a reason to do that. It's good enough. So you know, did an optimization round, looks about 6% slower than the core utils impl, which I am fine with, right? That's that. So, well, yeah, I mean, as I said, we are going to implement the md5 algorithm. We're going to implement the md5sum utility. We did just that, and I think we've succeeded. So if you have any questions, yeah, please leave them in the comment section or anything. And I think that would be it for today. So I'll see you on the next one. See ya.